Hi, everybody. Thanks to be here for this talk about an experiment in continuous deployment of JVM applications. I'm Nicola Frankel. It's my pleasure to be here at JDD. Well, I would have even loved better to be here like on site, but unfortunately this year it's not possible. So this is my first time at JDD. I've been a developer. I've been, doing a lot of technical roles in my career. And as I mentioned, since 1 year and a half, I'm working as a developer advocate, which gives me time to think and to let's put my not crazy but creative ideas into something constructive, trying to do prototypes and proof of concept and this kind of stuff. Right now, I work for a company called Hazelcosts. Hazelcosts, we have two products. The first one is what we call an in-memory data grid, and you can think about an in-memory data grid as a distributed data structure. So the most used structure is probably the map. And if you are a Java developer, you are used to have this interface where you put stuff into the map and then you get by key. And what we are doing is we are doing the same stuff. We have like a very close interface, but then everything is distributed, so you don't see the complexity of all distributed systems. The second product that we have is called Hazelcost Jet, and since I will showcase it in the end, I won't talk about it further. Continuous integration. I hope that everybody who is listening, everybody who fancies himself or herself a developer is doing continuous integration. I hope nowadays it's a given. And continuous integration is the fact that once you have worked on something, then you want to merge it with the rest of the work of your team and make sure that compilation work, that unit tests, they run as well. Then you might, depending on your situation, create the package, then do some more testing, which in that case would be integration testing. And perhaps packaging is not enough because you are using Docker or Kubernetes or whatever. So you put that into the container, and then the package or the container, you store it into a registry. And I hope really, and that's bad that there is no feedback when I'm talking to my screen, but I will probably, in the same room, I'll probably ask, and a lot of hands will say, yeah, we are doing that, and that's fine. However, I see recently a lot of CI/CD conflating the term that CI and CD are all the same stuff. And as I mentioned, where continuous integration should be the norm, and probably is for most people, for most developers, continuous D is one or two levels above. So first, there is no such thing as CD. There is either continuous delivery or continuous deployment. So please don't use the term CD because it means nothing. Or worse, it might mean something to you and something else to the people you're talking to. So continuous delivery is a process that after continuous integration, you've got your package or your container, and then you put it in the environment where it's ready to be deployed. And then you push a button, or in general, you ask the business, hey, sir, is it okay? Yes, no, yes, okay, let's go. And then it's deployed. So you have this completely automated pipeline up until deployment. And continuous deployment goes a step further where there is nothing manual. Everything is automated from the commit on, the tests, the creation of the package, the deployment, the test, everything is automated. So continuous integration, everybody should do it. I'm a firm believer that continuous deployment, not a lot of companies in the world do it because it requires a very mature environment. And when you are doing continuous deployment, what you want to avoid is downtime. Because if you deploy and meanwhile you break the production environment, it doesn't work that well. Your business won't be happy. And we have an issue in the JVM world, Java, Clojure, Scala, Kotlin, whatever, is the traditional JVM deployment model is you start the JVM, you deploy your new jar or your war if you are using an application server, and you start it again. And of course, there is downtime. And downtime is bad for at least 3 reasons. The first reason is engineers, in general, they don't like downtime because, well, that doesn't look that great on their resume. Like, if there is the choice between a company that is doing continuous deployment and a company which is not doing continuous deployment, you will probably try to work for the first company, because then you can say, hey, I've been doing continuous deployment, and that looks nice on your CV. The second reason is that most people nowadays, they expect no downtime. Like, if you have parents, if you have like family or friends who don't work in IT, they are not used to downtime when they are using Google, when they are using Facebook, when they are using, I don't know, Amazon. None of those companies have ever displayed a screen where they said, hey, sorry, please wait a few minutes. We are getting back very soon. Their genes, their maturity makes them able to deploy completely to production with no downtime. So people expect it. And the third reason is I took the example of Amazon. Like, every time Amazon switched off their store, then people would buy it elsewhere, and they don't want that. So every time you switch off your application, if it's an e-commerce application, if it's a sales application, then basically you are not saying at that moment, and your customers, they go somewhere else, and you want to avoid that. So, like, stopping closing the shop, closing the application, having downtime is not a good idea in most cases. Then you can tell me, but hey, we already have zero downtime. You don't know about blue-green deployment. Well, I know a bit about blue-green deployment. So this is blue-green deployment. You have the green environment, which right now is production. So people, when they are making purchases or interacting with your application, they are routed to the green environment and everything is fine. Meanwhile, the IT is releasing the new version of the application on the blue environment. And the blue environment, from a hardware and networking perspective, is exactly the same as the green environment. And there is no production and pre-production. There are two different production environments, and then you switch from one to the other. And when everything is ready, then the router is switched from the green environment to the blue environment. And thus there is no downtime. And of course, if I explain it to you like that, it's very easy, it's simple, everybody can do it. But there are a couple of problems. The first is, well, if I tell you, hey, now we are ready to go, how long does it take for the router to switch from the green environment to the blue environment? Is it instant? Is it a few seconds? There might be some latencies, there may be some cache somewhere. So it's not instant. There might be a slight issue. Now, bigger issue is, what are you doing with the people who are already on the green environment? So you have started putting items in your cart in the green environment, and somebody deploy the new version, and now I am switched to the blue environment. And what should I do? So if I have two people, perhaps I can migrate the data from the green database to the blue database. But if I have, and let's say, hundreds, thousands, or 10,000 of concurrent users from one environment to the other, the migration is not instant. So I will be switched to the blue environment, and I will lose my card in the process, which is probably not what we want. So one way to cope with that is to have a single database that is shared between the green and the blue one. But then we have another issue, because at that point, what are we doing if we need to change the database schema? And handling the database schema is a talk, changes is a talk in itself. And then it's not only the database, but what about session data? I know that everybody is doing stateless workloads, but that's not really true. like because we need to take the course into account, or the authentication, or this kind of stuff. So it works, but there are a lot of issues. And comes Kubernetes, and Kubernetes tells you, hey, but you know about rolling updates. So we have this deployment, we say we have 3 replicas, and then we make a rolling update from version 1.0 to version 2.0, and everything works magically. Well, the same problem applies. State is an issue. So session data, database data, this is not resolved by the Kubernetes deployment object. And all those solutions, both solutions, they require you to have different nodes. And I am a JVM guy, so what if I told you that you could change the bytecode inside the running JVM with no downtime, and you don't need multiple platforms, you just need one single JVM? That would be really, really cool. And that's what I'm trying to explain to you in this presentation. So the first thing is we will have a look at the instrumentation API. And the second is we will have a look at the attach API. Then we will try to bring everything together with some streaming engine. And finally, if the demo gods are with me, I will try to impress you with a demo. Java agents. If you have been working in Java for some time, you probably are familiar with Java agents. At least you have heard the term. And there is nothing magical in the Java agent. Basically, it's just a jar with a specific entry point and additional metadata. And Java agents are part of something that is part of the JVM called the instrumentation API. And the instrumentation API actually allows to change the bytecode of running applications. There are 2 types of agents. In general, people are familiar with the first one, which is the static agent. A static agent is set when you start the JVM. So you add these -java agents, colon, and then the pass on the file system to the agent jar. This is the additional argument that you pass compared to the java-jar my.jar. This is the way that is used by classical monitoring systems that try to monitor where your code is doing. So basically, this agent will intercept the changes, will write a log file somewhere, or will send it to another agent that will aggregate the metrics or whatever. And most of the monitoring tools that I know of are made through agents. But actually, there is another type of agent. There is a type of agent that you don't need to set at startup time. So basically, you have a production JVM, you have a JVM running, it's not running in debug mode, it's running normally. And then you can attach another agent to this running JVM. And this is the scope of the attach API that I will show afterwards. For the moment, you must understand that, as I mentioned, an agent is just a jar with slight differences. So instead of having a main method, a static agent as a pre-main method, and a dynamic agent as an agent main method. Compared to the main method, which only has arguments, we see that there is an additional parameter called instrumentation that will be passed by the JVM. And on the manifests.mf, for a static agent, you have the pre-main class, and for the dynamic agent, you have the agent class. And of course, that said, nothing prevents you from having an agent that is can be used both statically and dynamically. If you have both methods and both entries in the manifest. Instrumentation has 2 main use cases. The first is you can change the implementation of the class. Of course, there are limitations, and I will touch them afterwards. Also, you can do automatic transformation of bytecode, and that we won't be using in this presentation. And this is actually the whole of the instrumentation API. You have the instrumentation API. As I mentioned, you can add some automatic transformers. It's just for reference. It's here, but we won't be using that. What we will be using is this method called Redefine Classes. And you can see it takes a var of class definition. And the class definition is just a class with an array of byte. And this array of byte is basically the bytecode itself. So if I have a class and I have the contents of the compilation of the dot class, then I can take both, create a class definition, and change the running class inside the JVM. That being said, we need something. I mentioned the Attach API, and the Attach API is the API that allows you to have a running JVM and to add an agent at runtime. And the good thing is it doesn't need to run in debug mode. It needs two things. The first thing, it needs to run on the same system. And the second, it must know the PID of the production JVM. Bearing that, there are only those two requirements. Nothing else is necessary. And this is the Attach API in Hotspot. So basically, you have the virtual machine, which is an abstract class. It offers this static method, attach, and the ID here is the PID of the virtual machine I want to attach to. And once I pass it, I got an instance of virtual machine, and then I can use the load method, pass the path to the agent, plus some options if I need it. And that's all. And now I need something. I need to be aware when there is a change in the bytecode. And then I need to take the bytecode and to move it somewhere. And bytecode in that case is just data. So basically, we can use every way that we know to move data around. And there are two main models, the batching model, and I think that everybody knows about batching. You take data from your main database, you transform it, and you put it into your analytics database. I think that's the main use case of batching. Batching is good when you have bounded data. It can be huge amounts of data, then you go to our big data, but anyway, it's bounded. Streaming, however, means it's unbounded. So you don't know how much data you will be moving around. And that's exactly what we want, because actually there might be changes coming afterwards, and probably there will be. So basically it's like a Java 8 stream, an unlimited stream of events. In that case, it will be an unlimited stream of changes of bytecode. So we need a stream processing engine, and better an in-memory stream processing engine, because some of them are persistent, so you are persisting the data, but here we are just interested in getting the bytecode and putting it into the running JVM. So there is no really need to persist it. There are clouds, stream processing engines, so Amazon Kinesis, IBM Stream, Google PodSub, probably you might be already using some of them. Or they are also on-premise. You might know about Apache Flink or Hazelcast Jet that I will be showing afterwards. I also would like to mention something called Apache Beam, which I find it's a cool idea. Basically, Apache Beam tries to be an abstraction layer over some of the other ones. So, for example, Hazelcast Jet is an implementation of Apache Beam as well. I think it's a really cool idea. Of course, it tries to be an abstraction when there is no really any standard. So it might be quite leaky in some cases, but I think it's interesting. Hazelcast Jet. So Hazelcast Jet is an in-memory processing engine, and we offer it to you with the Apache 2 open source license. You can read the code, you can deliver issues, you can also make pull requests if you want. Everything is on GitHub. And it's available as a single jar. So if you want to start playing with it, you just add it to your dependencies. Then you can start Jet, and then everything will be inside the same JVM. So your application and the stream processing engine will run into the same JVM. It's very good for playing. However, if you want to start deploying it to production, you might want to have multiple nodes. And the problem with this approach is you will have the same number of Jet nodes as the same number of application nodes. So you cannot scale independently. So there is another way to use Jet, is to use it as a server, and then your application will be the client. The good thing with Jet is that it has a very unified API towards streaming and batching. So if you want to go from batching because you are more familiar with it, and afterwards you say, oh, but I want to start doing streaming, then there is just one single line of code that you add, and then you bridge into this other streaming world. Though it's a streaming engine, it has the power of like extract, transform, load that you all know from batching. So here are what we call sources, and you can see usual stuff like Kafka, like IMDG, the file system, database, or even more database events, like this change data capture with the Debezium. And then you have the targets, and again, it's Kafka or databases or the file system or whatever. In both of those cases, if you don't have the right source or the right targets, there is an API to let you create your own. So nothing prevents you from having a source that reads from a web service, for example, which I did in some other talk. And then meanwhile, in the middle, you've got this distributed system. So you can scale it up to your heart's content, because you need, I don't know, to do filtering on a lot of data, and you have a lot of memory, and you have a lot of nodes available. So you put as many nodes as possible to be as fast as possible. Mention also that in general, when you are doing transformation, either the transformation is completely self-contained. For example, you want to filter out some stuff, but sometimes it's not the case. Sometimes you need to access data to see, hey, if this data is found, or to take, for example, reference data. So you have this, I don't know, person, and you have only the ID of the person, and you want in your stream later on to have the first name and last name, and you need to check the database. The problem is every time you make a database access, then it takes a lot of time. Then you lose the benefits of being in memory. You lose the speed of the in-memory computing. So what you can do is you can load your reference data into IMDG, and then because Jet is made to work with IMDG, and IMDG also is in memory, then everything is in memory, and you can like enrich your stream in a much faster way. Now everything is set. I've told you about the instrumentation API, I've told you about the attach API, I've told you about the stream processing engine, and this is our design in the end. So we have this production JVM, and this production JVM runs the application. So you have the application running, and now we want to make changes to it. First thing, we will create a Jet job, so running into a second JVM, the streaming JVM, that will check the changes for the source class. And when it sees that there is a change, it will put that into IMDG, so into this in-memory data grid. And now we have this third JVM, the injection JVM, that will take the jar, and through the attach API, will update the production JVM so that the application can subscribe to changes in IMDG. So every time the Jet job may put something in IMDG, the application will know about it. So it will be able to load the new bytecode, and because of the instrumentation API, to change the running bytecode. This is another way of looking at it. This is a sequence diagram. So we have this jet job, and it will continuously loop to read the source class. And if there is a change, because it would be completely stupid to reload the bytecode if there is no change, we are checking if there is a change in the Hazelcast map. If there is a change, then we will put the bytecode there. Then we will load the agent attached to the production JVM. The production JVM will subscribe to the changes. And when there are changes, it will read the changes and reload the bytecode. So now it's time for some demo. Perhaps there are questions meanwhile. No questions. No questions is good and bad at the same time. Okay, so here I have my main application, and my main application is just a simple servlet that I will launch with Tomcat. I will launch it like this. Amazing. And normally here, if I type hello, I can see that it tells me hello world. So here, of course, here I'm hosting that on my machine, but let's imagine that this is the production environment. So I won't touch it ever again. I close it, nothing happens. And then I will have this stuff. Here I have a copy of the hello servlets, and that will be the source for my changes. So this is what I want if I change something here. I want the bytecodes to be read and updated into the production JVM. I have also the job. So now, I'm sorry, but I've written some Kotlin because I love Kotlin, really, really, I love it. So I have this job called pipeline, and pipeline basically will read from something called classes, and basically classes is just like changes from my file system. And I will dump it into the log just to be sure. Of course, you don't need to do that, but you know this is a demo. And then it will check that there are changes. And if there are no changes, then it will filter those events out. And then I will write everything into the IMDG map called bytecode. So this is a job. Then I have the agent. The agent is doing the following, is doing, hey, I will get the map called bytecode, and I will add an entry listener. And basically what this entry listener does is it will check for changes. And when there is a change, it will get the class. So in the map, the key is the class name, and the value is the bytecode, so the byte array. And I will just call the instrumentation redefine classes that I've talked about just before. And again, instrumentation is, I'm able to access it because there is this agent's main method. This has already been compiled. And finally, I will need to attach it, and attaching it uses the attach API. And as you can see, it's very, very simple. I will need the PID. So instead of having to check the PID every time, I've written a small routine using this process handle new API to get the PID of the running JVM. So the one that ends with main, or as it calls bytecode stream.main. So the one that is right now running here. And I only need to pass the path to the agent. So I can show it to you. It's here. So I've already compiled it, packaged it, and it's here. It's just this one that we just saw. And that's all, folks. So now I will run the jet job. And you can see, as I mentioned, I output just to be sure that something is doing, and then I will attach the agents dynamically to the running JVM. So now the agent has been attached. So the JVM, the injection JVM stops. And now I just need to make changes here. Compile it. I didn't see if it was compiled or not. I knew it. It's not compiled. It's here. This one should be compiled. So it's source. Okay, let's go back. That happened to me previously. I will start again everything because obviously something is not working. 2 seconds. I run this one. Yes. Now I run the jet job. And I attach. And now I run that stuff. I compile it. Okay, so I will show you the place where it works. That's the second time it doesn't work in front of me, in front of the audience. That's not a good feeling inside for me. I don't know. I tried everything. That's fine. Just trust me that it works. So this demo, which failed but should have worked, has some limitations anyway. The first thing is there is no version tagging. When you are doing traditional releases, so you take the jar and you tag it on GitHub and you tag the jar as well, you know which version is running. When you are doing continuous deployment, it's much harder to know exactly what version you are running because you didn't deploy the whole package. You deployed just like streams of changes. So this is a limitation, obviously. The first I didn't do because I've been too lazy is I didn't try to load new classes. I'm just having a class that is already loaded and then I try to change it. You can work that out for yourself. You can try to load your class. And finally, the hardest limitation there is the Redefine Classes itself has some hard limitations. So for example, you cannot add, remove, or rename fields, existing fields, or do the same with methods. You cannot change the method signatures. You cannot change the inheritance hierarchy. So it's pretty limited. You can mostly change the body, the implementation body. It's good enough for bug fixes and stuff like that. You might even think that instead of having a rules engine, those huge beasts which allows you to define in a pseudo language some business rules, then you could have like traditional Java code and then do the changes like that. There are also some improvements we could define. So instead of running from my local machine, I could stream it from a CI job. So I could have a source folder in the CI job and check the changes from here instead of checking the changes from my machine. Or I could also add additional metadata in each class. For example, I could have a git tag, so I could know, perhaps I don't know which exact version I have in production, but I would know that this class is version 1.2.3 and this class is version 1.2.5 and this kind of stuff. And finally, to bypass the limitation of the Redefine class method, what I could do is to have a specific class loader, a custom class loader. So if you have been doing the Spring DevTools, you know that Spring DevTools allows you to make changes to your code, which is running on your machine, and then instead, if there is an incompatible change, instead of restarting the whole JVM, what it does is just discards your code, because your code has been loaded in a dedicated class loader. So there are two class loaders. One is for your code. The other is for the whole dependency hierarchy. And in general, when you code, the dependencies are very stable. So you keep this class loader and you just restart the new one. And this is very, very fast compared to restarting the whole JVM. So this could be an improvement, of course. So thanks for your attention. You can read my blog where I publish weekly blog posts. You can follow me on Twitter. And if you want to make sure that I didn't lie to you, that it works as expected, because in general, you say it works on my machine. Here, it doesn't work on my machine, though it worked Monday. So fun stuff always. Then you can try to grab the code by yourself and try to do the same on your machine and check for yourself that it works indeed. So perhaps there are questions now.